Teams ship models that crumbled the first week in production because the rare cases were scrubbed from the data. The mistake is thinking an outlier is automatically noise, or a typo instead of a clue about how the data are actually generated. Mathematically, trimming extremes rewrites the distribution, drags the average toward the middle, shrinks the spread, and can let a lone extreme point steer a fitted line, or worse, erase the very signal you are supposed to detect. You are handed a messy dataset of transactions and failures. You delete the weirdly large values to tidy things up, and quietly set up a report and a model that will miss the very failures your team most needs to predict. Here's the mental model you actually want. An outlier is not a property of a point by itself. It is a statement about that point under a specific model of the data. Call a point an outlier only relative to a story about how the data are produced, a distribution shape you are willing to bet on, and a measurement pipeline you trust. If your underlying model changes, the identity of outliers can flip. The discipline here is to make your model explicit instead of blending eyeballing, convenience filters, and wishful thinking. Consider an online store where orders cluster around modest amounts, but from time to time, a company places an order worth $50,000. That big order might be a Keystone client renewing on an annual cycle, a corporate gift program, or a bulk purchase after a marketing blast. It might instead be a merger of separate orders in the database, a mistaken unit conversion, or a duplicated record. The raw number is not the point. The generating story is. Treat it as a nuisance, and you will misstate revenue, risk, and seasonality. Treat it as sacred, and you will allow flawed data to contaminate everything else. The beginner mistake is to treat an outlier rule as a broom. Anything beyond a canned threshold is removed quietly and without documentation, as if that were neutral pre-processing. This confuses cleanliness with truth. Removing points changes the data. You must justify that change with arguments about process, not with the vibe that a plot looks nicer without spikes. The cost of that mistake shows up in every summary that depends on distance from the center. A simple average becomes fragile. A few high or low values can yank it around. Variability looks small and safe when you race extremes, and you design capacity or budgets that fit the cleaned history instead of the world you live in. A regression line pulled by a distant point can produce a slope that predicts nonsense outside the middle range. And an anomaly detector taught that the world has no extremes will cheerfully wave them through. There's a correction, and it is not complicated. Build a small, repeatable checklist that separates errors from rare, but real cases. First, check for measurement and recording problems. Impossible strings or timestamps, broken encodings, swapped units, truncated values at system limits, duplicated rows. Then check for wrong population records, internal tests mixed with production data, synthetic benchmarks, or maintenance entries. Only after you have ruled out the mundane sources of weirdness do you ask whether the tail behavior of your domain plausibly produces that kind of observation. Now bring in robust summaries. The median resists extremes because it cares only about order, not distance. It tells you the typical value even with noisy edges. The interquartile range measures spread from the middle half of the data, shrugging off the tails, which is what you want when tails are untrustworthy. Trimmed or Windsorized means, which either drop or cap extremes, reduce the influence of the far ends without throwing away your notion of an average, but they need to be declared and justified. These are tools to describe the center and spread when you suspect that the usual distance-based summaries are being gamed by a few points. Visualization clarifies your thinking when you use it to interrogate assumptions. A histogram shows mass in the tails and whether the center is skewed. A box plot translates the middle and tails into a small, interpretable summary that can highlight a departure from the typical spread without resorting to formulas. A scatter plot is your friend in regression. Leverage is about being far in the input direction, and influence is about changing the fit when a point is present. Put axes on a logarithmic scale when magnitudes vary across orders, and you will often see that what looked like a spike is part of a smooth tail. Domain structure decides whether an outlier is an error, a separate population, or the thing you care about. In many business settings, the edge cases are the profit or the loss, not clutter. In safety, healthcare, security, and reliability, the unusual event is the target. If your model explicitly aims to predict or detect those events, removing them is sabotage. If instead Your goal is to understand the typical day-to-day pattern. Keeping them in the same pot will blur your picture. Put bluntly, the definition of outlier is conditional on the question you're answering. When you fit a line or a curve, a distant point can become the shepherd of the slope. Leverage is about where a point sits in input space. Influence is about how much the fitted relationship would change if you took that point away. You do not need fancy measures to get the idea. Refit after removing each point in turn and see how predictions shift. If the line flips or the intercept jumps when a single record is excluded, you are not learning a stable relationship. You are orbiting that record. Weighting schemes, robust loss functions, or stratified models can reduce that sway. But the bigger question is whether the point belongs in the same relationship at all. There's a family of modeling choices designed to respect tails without letting them dominate. Robust regression downweights large residuals gently rather than punishing them quadratically, which keeps the fit responsive to the bulk while still noticing departures. Quantile regression models. Conditional medians or other quantiles directly, which is valuable when you care about the upper or lower envelope rather than the average. Anomaly detectors trained with heavier penalties on false negatives will keep their attention on the edges. None of these choices remove rare cases. They structure the influence of those cases in a way that matches your objective. Heavy-tail domains demand a different baseline expectation. Insurance claims, trading losses, web traffic spikes, fraud amounts, and environmental extremes do not behave like tidy bell curves. Tails are where the budget, the risk, and the design constraints live. In such settings, the question is not how to remove extremes, but how to model them well. Techniques from extreme value analysis do not treat the largest values as junk. They model the distribution of maxima or exceedances directly, acknowledging that the far end has its own regularities that you ignore at your peril. Mixtures make honest data look odd under a single model. If day shift mechanics and night shift mechanics produce different distributions of repair times, stuffing them into one pot will make each tail look suspicious. The right move is to stratify the data by the factor that changes the process and analyze each stratum with its own model. When you do that, many so-called outliers resolve into ordinary points for their own population. The principle generalizes. A point that is an outlier under a pooled model may be ordinary under a conditional model that acknowledges the drivers of variation. Small samples are a special trap because they make rare events look impossible and common fluctuations look exotic. When you only have a handful of observations, the most extreme is still the most extreme. But that does not grant it cosmic significance. Your intuition may also underweight the probability that future samples will push past anything you have seen so far. In small studies, err on the side of documenting, but not discarding, and build your uncertainty into any claim you make. If you need to decide, design a follow-up data collection to pressure test whether the tail persists. Documentation is what turns judgment calls into science instead of folklore. Write down in plain language the criteria you use for flagging points, the checks you ran for errors, the domain knowledge you consulted, and the reason a point was kept, removed, or modeled separately. Keep a log of exactly which records were affected. Then run a sensitivity analysis. Compute your key results with all points, then with flagged ones removed or capped, and compare. If the headline numbers change meaningfully, you have learned something about fragility. Include that fact in your reporting. There's a simple operational habit that will save you grief. Decide your outlier policy before you look at the results you want to publish. If that policy depends on thresholds, set them by reference to domain constraints, not by chasing a cleaner plot. If the policy depends on diagnostics, specify the diagnostics and what constitutes a fail. Then stick to it, and if you must deviate, record and justify the deviation. This is not ceremony. It is how you make sure your choices are about truth, not convenience. Present both robust and classical summaries when the tails are suspect. Show the typical value using the median and the spread using the interquartile range, and compare that to the average and the standard deviation, which are more sensitive to distance. When those tell different stories, do not merge them into a vague middle. State plainly which better suits your use case. For forecasts or designs where rare peaks matter, present stress tests that hold the center fixed and vary the tail heaviness. For causal questions, ensure that influential points are not driving a pattern that will evaporate under a more honest model. The cross-cutting idea is simple. Outliers are not stains to scrub away. They are hypotheses about mechanisms. Sometimes the mechanism is an error you can and should fix, Sometimes it is a separate population you should model on its own. Sometimes it is the rare event you must design for. Your job is to decide which world you are in and to let that decision shape your summaries, your models, and your reports. Next, we tackle correlation versus causation, the mistake that breaks most arguments. Because once you stop being fooled by outliers, you still need to stop being fooled by patterns that are not causes.